As we continue our discussion on inverse trigonometric functions, the first problem you see is find the exact value of the cosine of the inverse sine of 1/2. And what we've done in the past is we've had cosine and inverse cosine, or inverse sine and sine, but we've never had a mixture of the functions. And so that's what we're doing here. Now, I'll tell you why I'm going to approach this problem the way I do in a moment. But one thing that I notice, of course, is the inverse sine of 1/2 is an angle. And so I'm thinking here of taking the cosine of some angle that I'm going to call theta. So I'm going to let theta be the inverse sine of 1/2. And so then that means what I'm to find, we need to find then the cosine of theta. That's what we've got to do. That's what we call theta there. That's the inverse sine of 1/2. Well, what does this mean? When we say the inverse sine of 1/2 is theta, that means there's two things. One, it means if we take the sine of theta, we get 1/2. And it also means, okay, in addition to, it means that the angle theta, of course, has to be between negative pi over 2 and positive pi over 2. So if we look on a unit circle, here's what we're dealing with. Well, I'm sorry that that's lopsided. See if I can at least get some kind of a decent scale here. So let's assume this is where 1 is. And of course, this is where negative 1 is, and this is where 1 is, and this is where negative 1 is. So as I draw my unit circle, well, a little sloppy. Oops. A little sloppy. My bad. I apologize for that. But of course, we're looking for an angle that falls between negative pi over 2 and positive pi over 2. Now, here's what we know about that angle, though. That the sine of it is 1/2. And of course, that ends up being where the second coordinate is, and that's going to correspond to this angle. Now, let's kind of keep in mind that we have three important angles here that are kind of close together, and this one would be pi over 6, and this one would be pi over 4, and this one is pi over 3. Remember those relationships. So here's what we know then, that theta, from our conclusion here, theta is equal to the angle pi over 6. So keeping that in mind then, since we are to find, let's start from the very beginning, we are to find the cosine of the inverse sine of 1/2. And the inverse sine of 1/2 I called by theta, and we decided that theta was pi over 6, so what we're doing is finding the cosine of pi over 6, and we know that the cosine of pi over 6 is the square root of 3 over 2. And so we've completed our job, okay? Now, this works when this inverse sine or cosine of the value here happens to be the result, one of the special numbers we get, like 1/2, square root of 2 over 2, square root of 3 over 2. When we have that type of number there, then we can find the exact value of theta and then turn around, or the inverse sine of that value, and then turn around and use that and calculate the cosine or whatever we need to of that particular angle. In other words, we could find the angle theta exactly. But that's not always the case. And so in our next problem, we're going to see a need to take a different approach. And let's look at the next example here. As you see in this one, we're supposed to find the tangent of the inverse sine of 2/3. Now the issue here is the 2/3, and I'm just going to make a note over here on the side, because if I called theta the inverse sine of 2/3, that means that the sine of theta would have to be 2/3. And we don't have an angle that we know of, a value of an angle that we know of whose sine is 2/3. We did know one whose sine was 1/2, but not 2/3. And so this kind of leaves us in a bad situation. So here's what we're going to do. We're going to start out like we did before, though, and we're going to call this theta. Okay? So we have theta is the inverse sine of 2/3. Now, here's a little bit more information. That would tell us that 1, the sine of theta is 2/3, and 2, theta is between negative pi over 2 and positive pi over 2. But because the sine value is positive, that can only happen in the first quadrant. It can't happen if our choice is the fourth quadrant or the first quadrant. It can only happen in the first quadrant. So that tells us, actually, that theta is an angle between 0 and pi over 2. Now, if I think in terms of degrees, that's between 0 degrees and 90 degrees, okay? So we have an angle that could be the angle in a triangle. Now, here's what we do next. We look at a representative right triangle, is what we call it, okay? And we have an angle here that is theta. Now, we know from our discussions previously that the sine of an angle theta in terms of a right triangle is the opposite side divided by the hypotenuse. And so to get a representative right triangle, in our case, the sine of theta is 2/3. So we can think of the opposite side as being 2 and the hypotenuse as being 3. So that means this side would be 2 units and this side would be 3 units. Now, because this is a right triangle, then the Pythagorean theorem would work. And the Pythagorean theorem says what? It says that a squared plus b squared is equal to c squared. And of course, the hypotenuse is c, and we could call one leg b, and it's this other leg that we don't know. And we'll see in a moment why it's important to know that. So what we could do is solve for a, because we would have a squared plus b squared, and b is 2, is equal to c squared, and c is 3. So as we move this up here so that we have room, we would end up with a squared plus 4 is equal to 9, or a squared is equal to 5. Now, in this case, a is the length of a side, and so we couldn't have a being, we wouldn't say a is plus or minus the square root of 5. It could only be positive since it's a length of a side. So now we know that this side has a length of the square root of 5. So what? Okay, so what? Well, remember what we're trying to do. Okay, now we're ready to get down to business, because we're originally asked to find the tangent of the inverse sine of 2/3. And we called the inverse sine of 2/3 theta so that we could deal with it. And theta is part of this right triangle. And the tangent of an angle in a right triangle ends up being what? The opposite side divided by the adjacent side. And so in this case, the opposite side of the angle theta is 2 units long, and the adjacent side is the square root of 5 units long. So the only thing that we would need to be concerned about next is rationalizing this result. And so we would multiply this denominator by the square root of 5, and likewise the numerator by the square root of 5. And so we would get a fraction where we had 2 times the square root of 5 for the numerator, and square root of 5 times square root of 5 for the denominator is just 5. And so there is the result of finding the tangent of the inverse sine of 2/3. And we call this using a representative right triangle. Well, let's look at another one that is similar to this, and we'll do that on the next page. So as you can see, the problem here is we're to find the exact value of the secant of the inverse tangent of 6/7. And you understand exact value means without the use of a calculator. Okay, so the secant of the inverse tangent of 6/7. Now, the inverse tangent of 6/7 is an angle whose tangent is 6/7, and we don't know the special angle who has a result of 6/7. But we're going to go about what we've done before. Okay, we're going to say theta is the inverse tangent of 6/7, which tells us that if we take the tangent of theta, we get 6/7. And because this is a positive result of tangent, and the inverse tangent, that is theta, has to be between negative pi over 2 and positive pi over 2, well, that really says that theta has to be between 0 and 90 degrees, or 0 and pi over 2. Otherwise, we'd have a tangent value that was negative. That's the idea behind that. So here's what we know, okay? We know that the tangent of theta is 6/7, and that the angle theta is between 0 and 90 degrees. And so that can be part of a right triangle. So I'm just, again, drawing a representative right triangle, and I'm calling this the angle theta. Now, the fact that the tangent of theta is 6/7, and in a right triangle, we calculate tangent by opposite side divided by adjacent side measure. And to represent this angle in a right triangle, we can call the opposite side 6 units long and the adjacent side 7 units long. Now, we probably are going to need this hypotenuse length. And in fact, look where we are. Let's start so that we kind of see where we're headed. Okay, let's look where we are. We're asked to find the secant of the inverse tangent of 6/7. And because we call the inverse tangent of 6/7 the angle theta, then we need to calculate the secant of theta. But the secant of theta is the same thing as 1 over the cosine of theta. And so we need to calculate the cosine of theta. Now the cosine of theta in a right triangle is, see, the cosine of theta in a right triangle is what? Adjacent side divided by hypotenuse. And so it all comes down to us needing to know the hypotenuse, because we already know the adjacent side is 7, don't we? So we've got to come up with a hypotenuse, but this is a right triangle. So we could call this side A, this side B, and so we need the hypotenuse, which would be C, and we know because this is a right triangle, the Pythagorean theorem would be true, or C squared is equal to A squared plus B squared. And so C squared is going to be 7 squared plus 6 squared. And 7 squared is 49, and 6 squared is 36. And so 49 plus 36 is 85. And C, we would normally say, is plus or minus the square root. But in this case, C is a positive number because it's the length of a side. And by the way, 85 is 5 times 17, and both of those are prime, and so we can't simplify the square root of 85. Okay. So here's that hypotenuse. Well, then we're about done with this problem, because look what we're going to have here. We're going to have 1 divided by the adjacent side, which is 7, and the hypotenuse divided by the hypotenuse, which is the square root of 85. And so we're really being asked here for the reciprocal. What would we do? We would say 1 times the reciprocal of that divisor, and the reciprocal would be the square root of 85 over 7, or simply the square root of 5 divided by 7 is the result that we're looking for. Okay. So once again, that's the idea of using this reference right triangle, and we do that when the theta value is not one we're expecting to be a special angle. Well, let's finish this off with one that's going to follow the same line of reasoning, but the directions are a little different, and we're not dealing with numbers. So we'll look again at that on the next page. You can see here the problem is stated as to write cosine of the inverse sine of u as an algebraic expression containing u. Now the issue is algebraic expression. And when we see that, then that's implying that we don't want to have any trig functions or inverse trig functions involved. It would just be things like squaring or cubing or adding or subtracting or square rooting, algebraic operations. And we approach this much like the ones we've been dealing with when we create this reference right triangle, representative right triangle. So when I'm looking at the cosine of the inverse sine of u, I once again remember that the inverse sine of u is really an angle, and I'm going to call it theta. Okay, so from that information, here's what I've got. Theta is the inverse sine of u, and that means if I take the sine of theta, I get u. Now, when we start building a representative right triangle, and that is a right triangle that represents this one single relationship we have, we're going to call this angle theta, and we're going to, of course, this is a right triangle. Now, in general, the inverse sine, the sine of an angle theta, we calculate by saying the length of the opposite side divided by hypotenuse. In our case, we know that the sine of theta is equal to u, so we need to write that u in form of a fraction, and the easiest fraction we can use is u over 1. So that allows us to represent the opposite side by u and the hypotenuse by 1. Okay, and we kind of had to manufacture that idea. Now, we're going to use the Pythagorean Theorem again, where we're thinking of this as side A, and of course this is side B, and this is the hypotenuse. And so from that information, we have that a squared plus b squared equals c squared, and in this case, b is u. So this is a squared plus u squared is equal to c squared, and c is 1. So that ends up being, we're solving for a. That ends up a squared plus u squared is equal to 1, or a squared is equal to 1 subtract u squared. But since a is the length of a side, then we know since a squared is 1 minus u squared, a itself is the square root of 1 minus u squared. So that's how we can measure this adjacent side. Okay. Well, where are we? Back here now. We have the cosine of the inverse sine of u, and the inverse sine of u is what we call theta. So this is really the cosine of theta. And the cosine of an angle in a right triangle is the adjacent side divided by the hypotenuse. So in this case, that adjacent side is the square root. It's the a, isn't it? The square root of 1 minus u squared. And the hypotenuse is 1. And so when we simplify that expression, it's simply just the square root of 1 minus u squared. So we've written this cosine of the inverse sine of u in terms solely of algebraic expression. This is our answer. Okay. That's what we're looking for. Now you've got several examples like this, problems like this that you'll need to do in your homework. This becomes an important practice when we get to a particular level in calculus. Well, I hope this gets you started on your homework. Good luck.